Alright, here she is. She's starting at the top. There she goes, free fall, right to this point. At this point, the bungee cord starts to pull upwards, and it slows her down. Let's look at how that appears on these graphs. I should have asked this question in the lab, but I didn't. First of all, in the vertical direction, I have 6 graphs here for the horizontal and the vertical direction. So when she started at time 0, she certainly was accelerating downwards. And then when the bungee cord started to stretch, the bungee cord is accelerating her upwards. It's slowing down her downwards velocity. So she must be accelerating upwards there. Then it snaps. So through this phase, she's accelerating upwards because her downwards velocity is being slowed, and it snaps. Because it snaps, she's now, from this moment onwards, in free fall. So her acceleration immediately drops from bungee cord acceleration back to the acceleration due to gravity. Then what happens? First the bungee cord, then she hits the water. In a very short moment, she comes to a sudden stop. That looks like on our graph. So the acceleration due to the bungee cord was upwards, slowing her down. The acceleration due to gravity downwards kicked in. She hit the water, and for a very, very brief moment, her acceleration was dramatically upwards to slow her down. If it wasn't, she would have kept going downwards. So the acceleration had to have been upwards. And once she's in the water, she's at the surface, and she doesn't accelerate anymore. All right, how does that look in terms of velocity? Well, she started at 0, and she steadily went downwards. She slowly sped up downwards, down, faster and faster. And that the slope here matches the negative value for acceleration. The slope in this section matches the dramatic positive acceleration. So she went, her downward velocity rapidly decreased, maybe to a slow downward velocity. Maybe the rope just stopped her at 0. I actually think it brought her up a little bit. But as soon as it snapped, her velocity was downwards again. And when she hit the water, it quickly dropped to 0. And when she was in the water, basically she had no velocity in the vertical direction whatsoever. All right. And if it wasn't for the bungee slowing down her maximum downward velocity from here to here, she would have hit the water. Basically, without a bungee cord, velocity would continue to drop until she hit the water, and she would have been dead meat. So that the bungee cord slowed her down as much as it did saved her. Even after it snapped, she fell from that point down to the river, and she hit the river with a large downwards velocity, but not so much to kill her. If you jump off of a bridge this high, unless you take special precautions and you're very lucky, you are dead. So given that her acceleration is first downwards due to gravity, then upwards due to the bungee, downwards due to gravity, upwards due to water, taking her down, up, and down. What's up with how does that affect her position? Well, her position starts at the bridge. I guess we could say the bridge. Let's say the bridge is 0 and the river is down below. So let's start her here. Acceleration kicks in, so it's going to be parabolic downwards to here. So that's parabolic downwards. Now we have an upwards velocity, a velocity, increasing velocity, positive acceleration. Now we have parabolic upwards. Now decreasing velocity, negative acceleration, parabolic downwards. Actually, this should probably be a little steeper downwards. As she hits the water, she comes up, and she basically remains at the same level, which is the surface of the water. Okay, how does that look? All right, so parabolic downwards, parabolic upwards, parabolic downwards, a sharp but small parabolic upwards as she plunges into the water and comes back to the surface, and then she remains at the surface. So here she goes, falling down, being pulled upwards, falling down, being pushed upwards by the river, maintains her position at the river. Horizontally, you can argue about not much changes horizontally until she hits the river. Then she starts to move steadily downriver, and she starts to accelerate a little bit into the rapids. Velocity in the x is either 0 or very close to 0. It bumps up a little bit as she hits the river. She's now basically going the speed of the river, basically at constant velocity. As she approaches the rapids, her velocity picks up a little bit. The river does increase. So in the horizontal direction, there's no acceleration. There's a brief moment of acceleration as she enters the water and the river picks her up to river speed. Then as she's in the river, no acceleration. And then the river seems to speed up a little bit as it approaches the rapids. Okay, I have that's all.